In this final sequence, related to dependent sources and amplifiers and the small signal method, let us look at the small signal circuit technique for analyzing such circuits. As a first step, as is usual, let me go ahead and do a quick review of what we've covered in the most recent sequences, and then we'll go into the small signal circuit method. So we looked at a couple of things. Out here you see our amplifier, and we said that in order to get small signal operation, I'm going to boost my signal by some DC offset, and then I'm going to apply my signal of interest out here. All right, so my total input voltage VI would be a sum of the DC offset and the input voltage. So my notation was as follows. VA is my total voltage, small v capital A. Capital V capital A is my operating point value, and small v small a is the small signal value. The operating point value is also called the DC bias point or the DC offset. Then we said when we operated circuits like this, I could of course get a Vout versus VI relationship through a nonlinear analysis. This would be through the large signal analysis. And then from that expression, from that equation, I could go ahead and derive my small signal relation as follows, where Vout, the small signal response related to the small signal input, would be given by the slope of the function f of Vi evaluated at the DC input offset point. Okay, and I had shown you a geometric interpretation of this, which said that given a function, say VO versus a VI, where VO was some function of a VI, and it doesn't matter what the function looked like; it looked like this. The way you computed the relation between the small signal VO and VI was that you took the slope of the function at any given point, and then you multiplied the slope by the small VI, which is the incremental change about the x-axis and about the VI axis, and that would then give you the incremental change VO about the VO axis. Continuing with the review, we also looked at a graphical view of how the small signal response behaved. And in order to do that, we first chose for ourselves an operating point. Okay, we said we're going to operate the circuit at this point, which was at a DC offset VI, and the corresponding output offset was capital V, capital O. And so that resulted in my operating point right here. Then what we said we'd do is we'd pick a small signal perturbation around that point. So notice that I have a small perturbation, and this is my voltage small v small I, my small signal voltage. And in this example, I've chosen a triangular wave, and that's how time goes in this little diagram. And corresponding to that small signal input, I would get a small signal response given by a much larger triangular wave because of the amplification happening. There's also an inversion because of the nature of the transfer function here. Notice that, as usual, this is one boundary of my saturation region, and this is another boundary of my saturation region. Okay, so my saturation region is of operation is within here. So as long as I chose a bias point within that region, I would be able to operate reasonably well. Finally, I'll also show you how Vi and Vo behave on a function of time. So Vi was my small signal input, and V0 was my small signal response. And the key observation we made was that Vo behaved linearly. Vo was linearly related to Vi for small perturbations. Okay, so this was a view that we took, and based on an operating point right here. In the sequence today, we will look at how do you go about choosing an operating point. Okay, and we'll look at that in a few minutes. Let me continue with the review for now. We also looked at a mathematical perspective of the small signal, and recall that this was the input versus output transfer function. This was a nonlinear function. Vo was a function of Vi. Okay, so this was my Vo was a function of the input voltage Vi. Vi is the voltage here. Okay, so then we also looked at directly deriving the small signal response from the transfer function here. And as I mentioned earlier, derivation involves taking the slope of the transfer function at the point Vi equals capital V capital I, the operating point at the operating point, and then I multiplied that by small Vi. Okay, that gave me the small signal output. And then going ahead and taking the derivative, this is what I got. I got minus k times vi minus vtrl times vi, the small signal vi. So notice that the parameters k times vi minus vt had a couple of parameters in there related to the MOSFET. K was connected to the MOSFET and vt was related to the MOSFET. Vi was the operating point voltage and RL was a circuit parameter. And for reasons that you will find out today, I called K times Vi minus Vt GM, or a transconductance, and this is related to Vi, and it is constant for a fixed DC bias. Okay, we'll see more of GM today and really understand why we've been calling this GM, why we've been calling this a transconductance.